we're going to use an element argument to prove these two sets are equal to each other. If we look at the left-hand side, we have actually three sets, and we do in two operations among these three sets. And on the right side, we have still three sets, but we're doing union, intersection, these operations. And don't think the left side as three individual sets. We have to it's just like addition, subtraction. Think of A, B, C as numbers. After you add or subtract numbers or multiply, you will just get a single number. So the same thing here. The left-hand side is just going to be a single set. So we use the example we talked about in class. You can maybe think of the left-hand side, the result after you do intersection of B and C and union, and you're just going to get a single set. Let's call it M. So that's Math Club. And the right hand side, we do union first, two unions, and do intersection, and you're still going to get a single set. Let's call it say history set. So history club set. And so we are trying to pretty much trying to prove the history club equals the math club. And by the definition of two equal sets, what does that mean? It means when we say two sets are equal, it means the math club is contained in history club, and history club is also contained in math club. So that's the definition of two equal sides. So whenever we need to prove two sides are equal, we have to prove two sets, two directions. And that's the first thing. The second thing is, so in this case, this is our M. Let's call it M. The left-hand side set is M. The right-hand side is H. You don't really have to do that when you do the problem. What I'm trying to explain here is I use M and H to make the explanation easier and to help you see the left-hand side as just one set M. The right-hand side just as one set H. Because after you do all these operations, you're just going to get one set. Okay, so first step, we want to show the left-hand side is set contained in the right-hand side. How do we show that? So the left-hand side is instead of what is M? M actually is operation of three sets, and H is also operation of these three sets. So we want to show A union B intersecting C is contained in A union B intersecting A union C. And how do you prove? So next step is, how do we prove one set is contained in another set? And that's by the definition. So if you want to prove, for example, Math Club is contained in History Club. In other words, Math Club is a subset of a History Club. You have to prove every member of Math Club is also a member of History Club. And we use a variable x, the lowercase x, to represent a member. You can also call it an element. So that's why we call this proof argument element argument. So every member of Math Club, which is called an element also. So this is an element x in M. So every element, or any element, we use the symbol to represent any. For any element in Math Club, we need to prove X is also an element in History Club. So that if you can prove that, and then you proved Math Club is contained in History Club. Similarly, and you have to do the third case, the second case that you have to prove. How do you prove History Club is contained in Math Club? And you have to pick any element from History Club, any member. You need to show X, this member X is, or element X is also a member of Math Club, and then this will be proved. So let's try to do that. And first of all, so let's prove two directions. First, we're going to prove Math Club, which is A union B intersecting C, is contained in the History Club, which is A union B intersecting with A union C. And so that's the first step. Second step, we have to do the other direction. So first, I'm going to prove a math club is containing history club, which means let's take a look at how we prove one set is containing another right here. We need to pick a member from the smaller set. So let's pick a member. We use a lowercase x. We always you can use y if you want, but usually we use x. So I pick a member, x to represent the member in the math club, which is A union B intersecting C. Now my goal is to show x is in the history club. And how do we do that? If you want to prove that, that means you have to show, notice on the right side we have the intersection of two sets. So you will have to show that member x is in here, A union B, and this pretty much translated to n. And x is also in A union C. If you can show that, and then we get what we need. So let's see how we start with this. This is what we know. And what do we prove? Our goal right here is to prove that x is in A union B and x is also in A union C, because this will give us the conclusion by the definition of intersection, and it's like, you know, intersection. So that means we use a symbol to represent and. That will give us A union B intersecting A union C. So this is omitted because we have it in front of both. Now let's see how we get that. Again, by definition, what's the definition of or? Or, we know that definition of union means or. So you can pretty much replace this symbol with or. So by this, because x is in A or in B, so we get a conclusion. A is in, x, the member x is in A, or the member x is in the other one, B intersecting C. So now we got two cases, because A or means this case could happen, this case could also happen. So let's do it by two cases. So I'm going to call this case 1, I'm going to call this case 2. And start with case 1. Case 1, x is a member of A. That will tell us, so refer to our goal. So keep looking at our goal. These two are what we need to prove. So if x is in A, can I get a conclusion that x is also in the union of A and B? And that's of course true, because that definition of union B means if x is in A or x is in B, then x is in the union, because this means or. And here in case A, we already know x is in A, so of course x is in the union. If it's in one of them, it's in the union. And then when done similarly, we can also get, because x is in A, then x should also be in the union of A and C. Because if x is in A or in C, then x is in the union. And we do know x is in A in case 1, then it should be in the union. So now we get what we want. So if x is in both of them, then x should be in the intersection. In the intersection. And that's exactly what our goal is. So now let's do case 2. So in case 2, we know case 2, x is in the intersection of B and C, which means we replace the word in the symbol with and, which means x is in B and x is in C. So you can see in the proof, we just keep using the definition of intersection, the union. So intersection is and, union is or. What does this mean? If x is in B, of course, we can get x is in the union of A and B, because the definition of A union B means or. So if x is in A or if x is in B, then x is the union. And now we do know x is in B. So that means x is the union of A and B. And similarly, we know x is also, this should be in, x is in C. So x is also in A union C. the same reason, because if X is in C, X should be in the union of C with any other set. Now we can get the same conclusion. If X is in both of them, both this set and that set, X should be in the intersection of these two. So now we proved our goal. We started with, what did we start with? We started with, we pick a member from the math club, which is the left hand side. So X is a member, and we proved in either case X is going to be a member of the history club, which is the right hand side. So now we're going to prove the right hand side history club is contained in the math club. Now we're going to prove the other direction. So this is our history club and this is our math club. So we're going to prove history club is contained in math club. So we still use the element argument. So let's pick element X from the history club. You can still use the same variable X, or you can pick a different variable. So now we replace intersection with the word and. The conclusion we're going to get is we're going to get X is in, since it's in the intersection of A union B and A union C, which means X is in A union B and X is in A union C. So now we're going to replace the word. So we just replaced the intersection with the word and now we're going to replace the word union, the symbol union with or. So from the, well, I noticed that here, and means both will happen. So in not only this, but also that. So these two shouldn't be two cases, but inside here in the first condition, we will have two cases. So we get X is in A or X is in B. So union is replaced with the word B. And X is in A or X is in C. Now we take a look at here. In the first condition, we know X is in A or X is in B. So, well, let's just focus on the first condition. Notice that this is not an or, so we shouldn't actually consider C, X in C as a third case. So what I'm going to do is case 1, X is in A. Case 2, I would say X is not in A. Since we only have, so we have, if X is in A, so let's look at both conditions, and we get X is in, take a look at our goal. So let's write down our goal and what we need to prove. We need to prove, so we picked a member from the history club, and we need to prove the member is also in the math club. So I'm going to write down our goal up here. Our goal, we need to show the member we picked, X, is also a member on the right hand side, which means, and if we replace this with or, it's equivalent to say we need to show X is either in A or X in the intersection of B and C. So let's take a look. If in case A, it's very easy. If X is in A, and we already got what we need, so we can say if X is in A, then X is, you can say X is in A or X is in the intersection, which means X is in the union of A or B intersecting C. Again, that's just by the definition of union. If you have a member that's in one of these two, either in A or in B intersecting C, then it will be in the union. So, and we already, in case 1, we know X is in A, so that should be in the union of A with any other set. Now let's deal with case 2. If X is not in A, if X is not in A, then is X in B or C? Let's take a look at the two conditions. So we should notice that this, because of this word